Section 7.2 is on properties of exponential functions. Just as we saw with other functions such as quadratic, absolute value, and square root functions, the exponential function can also be transformed. So the parent function for an exponential function is y equals b to the x. Remember, what's unique about this is b, the base, is going to be a number, and my independent variable is the exponent. Where in most other functions we've seen, like in the quadratic function, we have our x is the base, or independent variable is the base, and it's raised to a constant power. So we can, as we saw in the last section, we can put an a in front of that, y equals a times b to the x. And if the absolute value of a is greater than 1, it's going to be a stretch. If the absolute value of a is between 0 and 1, it's going to be a compression or a shrink. And if a is a negative number, it's going to be reflected in the y-axis. And again, we have translation, so horizontal by h and vertical by k. So we can have y equals b to the power of x minus h. So h is going to tell me how much I move right or left. And then a plus k outside of that, that's going to tell me how much I move up or down. And this scary looking beast here is what it looks like with all of those transformations combined. So a stretch or a compression, a horizontal translation, and a vertical translation. Let's take a look at a couple examples and do some graphs. So we need to graph each function as a transformation of its parent function. So here you have y equals negative 2 times 3 to the x. The parent function is actually y equals 3 to the x. And this negative 2 here is going to give me a stretch. Oops. And a reflection. A stretch because it's a 2, and a reflection because the 2 is negative. But let's go ahead and graph our parent function here. So picking some values for x, okay, I'm going to choose negative 2, negative 1, 0, 1, and 2. So when I have 3 to the negative 2 power, that's the same as 1 over 3 to the positive 2, or 1/9. 3 to the negative 1 is going to give me 1/3. 3 to the 0 is 1, 3 to the 1 is 3, and 3 to the 2 is 9. Now I know it's not going to be possible for you to graph a y value of 1/9, but what that is it's going to get very close to the y-axis. Actually, let's go ahead and graph those points. So negative 2, 1/9, just kind of put it down there. Negative 1, 1/3. 0, 1, 1, 3, and 2, 9. So that's my parent for this, y equals 3 to the x. Okay. Now to do the stretch and the reflection, I'm just going to multiply my y. Whoops. Multiply each y value by a negative 2. So that's going to give me a negative 2/9, negative 2/3, negative 2, negative 6, and negative 18. So I'm going to use my original x value and my new y value. So negative 2, negative 2/9. Okay, I can't really graph that. Negative 1, negative 2/3. Oops, didn't stay there. Negative 1, negative 1/3. 0, negative 2, 1, negative 6, and this one's going to go off the graph. 2, negative 18 is going to be way down here. So then this is going to look like this. Okay, and again, my y-axis is my asymptote. It does not touch the y-axis there. So you can see that it's stretched a little bit, okay, and it is definitely reflected over the x-axis. Let's try one now that combines a lot of things, a lot of different transformations. And I know this looks scary, but we can do this. So we're going to start with our parent. So we have y equals 1/2 times 2 raised to the power of x minus 3 plus 4. So I'm going to graph my parent function, or start with my parent function, y equals 2 to the x. Make a little table of values for that. Negative 2, negative 1, 0, 1, and 2. It's a good starting point. And actually, I kind of know I'm going to need a few more here, so let's do 3 and 4 also. So 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, 4, 8, and 16. Now let's take a look at what we have here. So this right here, my A value is 1/2. So that's going to be a compression. Okay. And my -3 right here means I'm going to move right 3. And my +4 right there means I'm going to move up 4. So I'm going to go ahead and do my, my compression, and I'm going to multiply every y value by 1/2. So 1/4 times 1/2, that becomes 1/8, 1/4, 1/2, 1, 2, 4, and 8. Now you can see why I went up to 16. So let's go ahead and graph that one. So -2, 1/8. Oh, we can't really do that. We're just going to do something approximate like that. 0 is 1/2. 1, 1, 2, 2. That's kind of strange. 3, 4. Okay, now I'm seeing the exponential growth. And 4, 8. Okay. And again, it is kind of hard to graph it down here where it gets really close to the y-axis, but just make sure it doesn't touch. So that's y equals 1/2 times 2 to the x. I'm going to use that as kind of my parent function from there. Now I'm going to take each point on that graph and move it right 3 and up 4. And I think I'm going to change colors here just to make it a little easier to see. So each point, and maybe I'll start up here. I'll go right 3 and then up 4. Right 3, up 4. Right 3, up 4. Did that one. Right 3, 1, 2, 3, 4. That's going to be partway in between there. Those are going to be hard to do, but I can see it's going to go like this. And because I moved it up 4, instead of the y-axis being my asymptote, now the line y equals 4 is my asymptote. And I can just draw the rest of the curve so it kind of approaches that but doesn't touch it. Okay, that's the best way to graph something with transformations. Find the parent function, deal with any compression or stretch, and then graph that and then move up, down, left, right as you need to. Go back to black here. Okay. So far, all of the exponential functions we've looked at have had rational numbers as their bases. So for example, we've had y equals 2 to the x and y equals 1/2 to the x, and they have bases of 2 and 1/2 respectively. But an irrational number can also be used as a base. One of the most common is the number e. The number e is approximately equal to 2.71828 and so on into infinity. In the equation y equals 1 plus 1 over x, all raised to the power of x, e is the value that y approaches as x gets infinitely bigger. So as x gets bigger, the y value approaches this funky number e. Now natural base exponential functions have use e as their base. These functions are often used to describe continuous growth or decay, and they have the same properties as all of the other exponential functions we've seen. In the previous lesson, we had a formula for interest that was compounded annually, that is once per year. We can also compound interest continuously, and for that we're going to use a base of e. And here's the formula for that. So the amount in the account after time t is equal to the principal, or the initial amount that was invested, times e, our number e, raised to the power of r times t, where r is the interest rate and t is the time in years. Let's take a look at an example of that. So you have $1,500 in a bank account that pays 4.5 annual interest compounded continuously. How much will you have in the account after 15 years? So we're going to use our formula. A of t is equal to P times E raised to the power of RT. My principal in this case is $1,500, the amount that I initially put in the account. My rate is 0.045, and the time that I'm investing it is 15 years. So let's go ahead and plug those into the formula. So A of 15 is 1,500 times E raised to the power of 0.045 times 15. Okay, so 1500 times e, and when I multiply those two numbers in my exponent, I get 0.675. And now I'm going to put this into my calculator. You actually have an E button on your calculator. I don't remember off the top of my head right now, but you do have to hit perhaps the second, and it might be the divided by sign. Look for a little E right above one of the keys. So you're going to do that. You're going to hit E and then raise it to the power of 0.675, hit enter, multiply by 1500, hit enter again, and the amount in the account is approximately $2,946.05. So in this section, we took a look at how to graph some exponential functions using transformations, and we learned for the first time about the natural base, the number e, and how to use that in particularly in continuously compounded interest situations.